You can check out this question from JEE Mains 2025. These things are important considering JEE Mains. This was tested once in 2023 and 2020. This is the trick to remember this. Hi everyone, I am Ashlin, second year student at NIT Calicut. Today we will be challenging ourselves to revise the entire P block within 35 minutes. Let's start. We'll begin this video with a general introduction to the p block elements. You know that p block elements, the last electron enters into the outermost p orbital, and the number of p orbitals is 3, so the maximum number of electrons it can accommodate is 6. That too, in each orbital 2 electrons are there and of opposite spins. The valence shell electronic configuration would be ns2 np126. 126 depends upon the group. Let's say for group 13 it will be np1, and group 14 it will be np2. We'll see it when we see on each groups. Next up, we have oxidation states. The maximum oxidation state shown by a p block element is equal to the number of valence electrons. That is, let's take an example. For sulfur, the atomic number is 16. When you write the electronic configuration based on the Aufbau principle, you will see that the valence shell electrons are 3s2 3p4. Here 6 is the valence electrons and the maximum number of oxidation state will be 6. Next, what you see down the group is there is something called inert pair effect. When you move down, the s orbitals of the outer shell, they are very reluctant to participate in the bonding. This is because of the poor shielding of the inner d and f orbitals. We will understand this with an example. Let's take the group 14, and in group 14 you have carbon, silicon, germanium, tin, lead, and we'll consider the case of lead. The electronic configuration of lead is given by xenon 4f14 5d10 6s2 6p2, and you see that there are 24 f and d electrons. These electrons are poor shielders, and because of this the s electron gets attracted more towards the nucleus. When the attraction towards the nucleus increases, the ability to participate in bonding reduces. So in this case, s electrons are not willing to participate in bonding. Hence, the maximum oxidation state of lead in this case will be 2 and not 4. Generally, it is 4 because the total valence electrons is 4, but in this case, it will be 2 because of the inert pair effect. Next, we have the nature of oxides. The non-metallic oxides are acidic or neutral, and metallic oxides are basic. Moving on, we have anomalous behavior of first members in the group. The reasons for the anomalous behavior is small size, lack of d orbitals, and high ionization enthalpy. What are these behaviors? We'll see. First up, we have maximum covalency is restricted. Let's take the case of group 13, boron, aluminum, gallium, indium, thallium. And you see that in case of boron, that is a first member, there is no d orbital. But in case of aluminum, you have a vacant d orbital. So what it can do is it can expand its covalency and form more bonds. So in case of boron, the maximum covalency is 4, but aluminum can expand its covalency to 6. You can see over here in group 13, boron and aluminum. And even in group 14, when you are seeing carbon's maximum covalency is 4, but other elements, silicon and germanium, can expand their covalency because of the vacant d orbital presence. One more thing which you will be seeing is the p-pi multiple bond formation. It is the p-pi multiple bond is formed only by the first element. You can see carbon carbon double bond, nitrogen nitrogen triple bond, and carbon and nitrogen with other higher electronegativity elements, they form p-pi bond. But in other cases, the heavier elements, that is the elements down the group, they form d-pi or d-pi multiple bonds. But the stability of those bonds, as the d orbitals are in higher energy than p orbitals, they contribute less to the overall stability of the molecules than does the p-pi bonding of the second row elements. I hope you got this. To begin with, we have group 13 elements: boron, aluminum, gallium, indium, and thallium. We'll begin with the discussion of trends in this group. You know, ns2 np1 is the outer shell electronic configuration of this group, and starting with atomic radii, you'll see that apart from the regular trend boron, aluminum, gallium, indium, thallium, there is a switch between gallium and aluminum in case of atomic radii. This is because of the poor shielding of d electrons in gallium. Because of the poor shielding of d electrons, the outer electrons are attracted more towards the nucleus and the size decreases. Next, we have ionization enthalpy. It follows an irregular trend, and when you draw that in a graph kind of thing, you will get the graph as W. You can note that. You see that indium has the least ionization enthalpy and boron has the highest ionization enthalpy. You know, ionization enthalpy is the energy required to remove the outermost electron. So more and more it is attracted towards the nucleus, it is tough to remove and you require higher ionization enthalpy. Next we have electronegativity. In this you notice that boron and aluminum there is a slight decrease from 2 to 1.5, and next in gallium, indium and thallium there's a marginal increase. So from boron to aluminum it decreases and then it marginally increases. That's a trend of electronegativity. Next we have density. It follows the regular trend of increasing down the group. In melting point you can note that it is decreasing from boron till gallium and then it is increasing. Gallium has the least melting point and this was tested once in JEE Mains 2022. Next you have boiling point and it follows the regular trend of decreasing down the group. Next, we have occurrences of these elements. Boron is a rare element and it occurs at orthoboric acid, borax and kernelite. It has two isotopes, boron 10 and boron 11. And aluminum, it's the most abundant metal and you can find it in bauxite and cryolite. And nihonium, it is a synthetically prepared radioactive element. The half-life of its most stable isotope, it's just 20 seconds. So the chemistry of it is not known much, and gallium, indium, thallium are very less abundant metals. Physical properties of group 13, boron is a non-metal and all other members are soft metals and they have low melting point and high electrical conductivity. Speaking about boron, it is very hard crystalline, black color non-metal. It exists in multiple allotropic forms and it has a very high melting point due to its very strong crystalline lattice. This was tested once in 2023 and 2024. You can see this question. Statement 1 says boron is extremely hard, indicating its high lattice energy. And 2, boron has highest melting and boiling point compared to other members. This we saw earlier also. Melting point and boiling point, boron has the highest. So the correct option would be option C, which is both statement 1 and 2 is correct. Next we have chemical properties and under that we have oxidation state. Boron, it's very small size. Due to its compact nature, the ionization enthalpy, that is the energy required to remove the electron from it, is very high. So it forms only covalent compounds. And speaking about aluminum, it is very highly electropositive. Electropositive in the sense it is highly willing to donate its electron and it forms Al3 plus ions. And speaking about the stability of +1 oxidation state, as you know, the +3 oxidation state is the general oxidation state of this group because the valence electrons are, number of valence electron is 3. But as you move down the group, as we discussed earlier, that due to the inert pair effect, the inner s electrons are reluctant to participate. So as we move down the group, the stability of +1 oxidation state increases. That's what we see in the trend. Aluminum, gallium, indium, thallium. As we are moving down the group, the stability of +1 is increasing. And speaking about thallium, the +1 oxidation state is predominant and +3 oxidation state is highly oxidizing in nature. If it is oxidizing, it itself wants to get reduced. That is what it is signifying. Next, speaking about boron. Boron, BF3, BCl3, these are boron halides and they are Lewis acids because they complete its octet with the help of Lewis base. In this case, it is NH3, and BCl3 easily accepts the lone pair from the electrons of ammonia. Nitrogen has a lone pair above it. These two lone pairs are shared among boron and nitrogen and they form an adduct. In aluminum, they form dimers and attain stability. Next up, we have reactivity towards air. Boron is unreactive in crystalline form, but amorphous boron and aluminum metal react with oxygen and nitrogen and forms oxides and nitrides. You have to know that aluminum forms a very thin oxide layer over it, and the nature of oxides formed because of the reaction is acidic for boron trioxide, and aluminum and gallium oxides are amphoteric. These things are important considering JEE Mains and NEET. Indium and thallium forms basic oxides. Next we have reactivity towards acids and bases. Boron, there is no reaction, but in case of aluminum, it is amphoteric in nature. What does amphoteric nature means? It dissolves in mineral acids and aqueous alkalis. It reacts both with acids and base. Aluminum plus acid, let's take the case of dilute HCl. In case of dilute HCl, aluminum reacts with it and forms H2 dihydrogen. In case of HNO3, it doesn't react well. HNO3 renders aluminum passive by forming a protective oxide layer on the surface. Aluminum, there is an oxide layer getting formed, so HNO3, no reaction happens. And talking about aluminum plus bases, it liberates dihydrogen as the way it did with HCl. And next we have reactivity towards halogen. Boron, aluminum, gallium, indium, these form trihalides. But in case of thallium, it forms trihalides except TlI3. So, thallium iodide is not formed. Next, we have anomalous properties of boron. And why does this anomalous behavior come up? This is because boron does not have any empty d orbital, and hence the maximum covalency is restricted to 4. Trihalides of other elements other than boron, what they are covalent and they easily hydrolyze in water. They form tetrahedral compounds and octahedral compounds, but boron does not form that. Next, we have boron behaving as a Lewis acid and forming adduct formation. We saw this is in chemical properties as well. And aluminum, it is forming dimer and it is attaining stability. Boron forming adduct is also an anomalous behavior. I hope you got the group 13. Next, we have group 14. We will begin the discussion of group 14 with their occurrences. Carbon, it occurs as coal, graphite and diamond, and it is the 17th most abundant element by mass in the Earth's crust, and it has 3 isotopes, carbon 12, 13 and 14, and carbon 14 is a radioactive isotope. And for carbon, we have the entire branch of organic chemistry dedicated for its study, and if you need more videos on organic chemistry, let me know in the comments and subscribe to our channel for more contents like this. Next, we have silicon, which occurs as silica and silicates. It's the second most abundant element by mass. Then we have germanium, which exists only in traces, tin as cassiterite, and lead as galena, PBS. And you should note, ultra pure germanium and silicon are used in transistors and semiconductor devices. And flerovium, which also belongs to this group, it's a synthetically prepared radioactive metal. Next, we have the important topic, trends. And before that, you can note that Ns2Np2 is the general outermost electronic configuration of group 14, beginning with the ionization enthalpy. You generally know that ionization enthalpy decreases down the group, but in this case, in the last two elements, there's a slight increase in ionization enthalpy from tin to lead. This is because of the poor shielding of d and f block electrons, and this is called lanthanide contraction in this case. And melting point also, similar thing happens. It decreases down the group and there's a slight increase at the end from tin to lead. Next, we have covalent radius. This follows the general trend of increasing down the group. And electronegativity, it is almost same for all. Carbon, it is 2.5, and for silicon, germanium, tin, it is 1.8, and lead, it is 1.9. Density also follows the same trend of increasing down the group. Moving on, we have physical properties. All elements are solids, and carbon and silicon are non-metals. Germanium is a metalloid. Tin and lead is a soft metal. Next up, we have chemical properties. Firstly, we'll begin with the oxidation states. The common oxidation state of this group is +4 and +2. +2, you know, down the group, the stability increases because of the inert pair effect, that is inability of ns2 electrons to participate in the bonding because of the poor shielding of d and f block elements. And you can note, carbon and silicon, it is mostly occurring in +4, and germanium and tin, it's occurring both in +2 and +4. Pb, it is stable in +2. You should note that tin in +2 acts as a reducing agent that itself want to get to +4. Pb in +4 is a strong oxidizing agent, which means that it itself wants to reduce itself to +2. That's what we saw. Pb +2 is stable. Next, we see the reactivity towards oxygen. It mainly forms monooxides and dioxides. In this, you have to note the nature of these oxides. Carbon monoxide is neutral, and silicon oxide exists only at the higher temperatures. Germanium oxide is acidic, and tin and lead monooxides are amphoteric. Speaking about the dioxides, carbon, silicon, germanium, it is acidic, and tin and lead, it is amphoteric. For tin and lead, it is amphoteric in both cases. Reactivity to water, we have carbon, silicon, germanium, there is no reaction, and tin, when it is reacting with water, it forms the tin dioxide and dihydrogen, and Pb, it forms a protective oxide film, so there is no reaction after that. Next, we have reactivity towards halogens. It forms mx2 and mx4. Here are few things which you have to note in this. First one is SnF4 and PbF4 are ionic in nature. PbI4 does not exist due to the inert pair effect, and SiCl6 does not exist because of the large chloride ions. In this, what happens is Si is in +4 oxidation state, and so it is very small, and Cl, chlorine, is very big, and a small silicon is surrounded with large chlorine, which is very unstable system. That's why it is not existing, and this was once tested in JEE mains in 2021. And you have to note that germanium X4 is more stable than germanium X2, but lead X2 is stable than lead X4. There is an exceptional property for CCl4. Other tetrachlorides, they are hydrolyzed in water, but CCl4 is not hydrolyzed in water because it cannot accommodate extra lone pair from oxygen because it does not have empty d orbital. Other elements, the central atom can accommodate the lone pair of electrons from oxygen. You will see the example for SiCl4. SiCl4, the lone pair from oxygen is accommodated over there. When the reaction continues, you find SiOH4 getting formed. Next up, we have anomalous behavior of the carbon. The reasons are pretty similar: small size, high electronegativity, lack of d orbitals, and high ionization enthalpy. What are the anomalous behavior? Those are also similar. The maximum covalency is restricted to 4, and this carbon has ability to form p-pi bond with itself and other electronegative atoms like oxygen and nitrogen. Then it has a special catenation property, because of which we have the entire branch of organic chemistry. More videos are coming up on organic chemistry, so stay tuned for that and subscribe to our channel. And C bonds are very strong. That's why the catenation property of carbon is there, and as you move down the group, the catenation tendency reduces. Next up, we have allotropes of carbon. And in allotropes of carbon, the first one is diamond. Diamond has carbon in sp3 hybridization, and there are 4 sigma bonds forming a tetrahedral arrangement. It's a rigid 3D network, and it is the hardest natural substance known. Next, we have graphite. Graphite has carbon in sp2 hybridization, and it has a layered structure. And each layer has planar hexagonal rings, and which has 3 sigma bonds and 1 delocalized pi bonds. Because of this delocalized pi bond, it's a good conductor of electricity along the layers. Also, it is very soft and slippery, making it an effective lubricant as well. Next up, we have fullerenes. And in fullerenes, you see graphite, when you are putting in electric arc and heating with the noble gases helium and argon, you get fullerene. And these are the pure forms of carbon because there is no dangling bonds. And there is a special kind of fullerene called Buckminster fullerene, which has 26 membered rings, that is hexagonal rings, and 12 5-membered rings. Totally, there are 60 carbon atoms in it, and it's called C60. And you can see 6-membered rings can be attached with either 5 or 6-membered rings, but 5-membered rings can be attached only with the 6-membered rings. And it is aromatic in nature because there are 3 sigma bonds and 1 remaining electron which is delocalized, because of which the aromatic nature arises. And you have some other forms of carbon like carbon black, charcoal, and coke. These all are impure forms of graphite or fullerenes. And with that, we conclude group 14. Moving on, we have group 15. Nitrogen, phosphorus, arsenic, antimony, bismuth. The electronic configuration is ns2np3, and here you can notice that s orbitals are fully filled and p orbital is half filled, making the electronic configuration extra stable. Speaking about covalent and ionic radii, it increases down the group for a particular oxidation state, and you see that from nitrogen to phosphorus there is a considerable increase, but from arsenic to bismuth, due to the d and f orbital electrons, there's a small marginal increase happening. Next up, we have ionization enthalpy and electronegativity. This decreases down the group. Talking about physical properties, all elements in this group are polyatomic. Nitrogen and phosphorus are non-metals. Arsenic and antimony is metalloid, and bismuth is a soft metal. And physical state, you can see nitrogen is a diatomic gas and all others are solids. Only nitrogen does not show allotropy in this group, rest everything shows allotropy. And boiling and melting point, you can see the trend. In boiling point, it increases till antimony and slight decrease in bismuth. In melting point, it increases till arsenic and it then decreases. This is important. And speaking about anomalous property of nitrogen, nitrogen bond is a weaker bond because of the lone pair repulsions happening there. And it has a unique ability to form p-pi multiple bond with itself and elements with high electronegativity like with carbon and oxygen, and they cannot form p-pi d-pi bonding. Nitrogen's maximum covalency is 4 because there is no d orbitals for its expansion. You can check out this question from JEE Mains 2025. The maximum covalency of a non-metallic group 15 element E with weakest EE bond. They have given us weakest E bond. This signifies that it is nitrogen, because in nitrogen we know there is inter-electronic repulsions, and for nitrogen, because it doesn't have extra d orbitals, it cannot expand its covalency, and hence the maximum covalency is 4 for nitrogen. So the answer is 4. Next, we have chemical properties and oxidation state. The common oxidation states of this group is -3, +3, and +5. Down the group, the tendency to exhibit -3 decreases and +3 increases and +5 decreases. +3 increases because of the inert pair effect. And other common oxidation states are, nitrogen shows large number of oxidation states from -3 to +5. You can see in different compounds it's showing different oxidation states. And phosphorus shows +4 and +1 in some oxy acids. You can see in H3PO2 it shows +1 oxidation state. In nitrogen, when it is in oxidation state +1 and +4, disproportionation occurs. You can check out this reaction where it is getting oxidized and reduced at the same time. This kind of reactions are called disproportionation reaction. Even in phosphorus, all intermediate oxidation state, it disproportionates into +5 and -3. You can try out this question and you can put it in the comments. For solutions and notes, you can join our WhatsApp community or Telegram. We'll have more Google Meet sessions over there also. Make sure you join there. Next, we have reaction with hydrogen. These elements form hydrides of the form EH3. Stability, reducing nature, and basicity are important considering JEE mains. And you can see in stability, the stability of these hydrides decreases down the group. This is because the bond dissociation enthalpy is decreasing down the group and they can easily broke. Reducing nature corresponds to the ability to release hydrogen from the compound. Here you can see as the bond dissociation enthalpy reduces down the group, it can easily broke and it can easily release the hydrogen down the group. So the reducing nature increases down the group, and basicity, it decreases down the group. And boiling point and melting point, there is a different behavior with NH3. This is because of the hydrogen bonding which is present in NH3. You have to notice this was also once tested in JEE mains. You can try out this question and put it in the comments. We'll discuss the solutions later. Next, we have reaction with oxygen, which forms oxides of the form E2O3 and E2O5. Here, oxides in higher oxidation state is acidic, and that acidic character decreases down the group. You can check out this. Nitrogen and phosphorus oxides of the form E2O3 are purely acidic. Arsenic and antimony is amphoteric, and Bi, bismuth, is basic. Reaction with halogen, it produces halides of the form EX3 and EX5. Every trihalides except nitrogen trihalides are stable, and in case of nitrogen, only NF3 is stable. Speaking about pentahalides, all elements except nitrogen form EX5 because in nitrogen there is no d orbital to expand its covalency beyond 4. Next, with metals, these form binary compounds of -3 oxidation state like calcium nitride, calcium phosphide, etc. Talking about the covalent nature of the halogens, pentahalides are more covalent than trihalides because the polarizing power of +5 element is greater than +3. Now we have group 16, oxygen, sulfur, selenium, tellurium, and polonium. And the electronic configuration of these elements, you can see it here. And you can notice that NS2NP4 is the general outer shell electronic configuration of these elements. Talking about the atomic and ionic radius, it increases down the group. As you know, the number of shells increases down the group, the atomic and ionic radius increases. Both the ionization enthalpy and electronegativity decreases down the group. And as the ionization enthalpy is decreasing down the group, the metallic character increases because when the ionization enthalpy is low, it can easily lose an electron, hence depicting the higher metallic character. You have to note that the electronegativity of group 15 is greater than group 16 because we saw that in group 15, the electronic configuration was half filled and it is extra stable. And you can see the most electronegative elements in the periodic table. The order is like FOCl, NBr. Fluorine is the most and oxygen is the second most electronegative element. Electron gain enthalpy, you can see the trend, but oxygen, as it is very small, it cannot easily accept an electron into it. Hence, it has the least negative electron gain enthalpy. Negative electron gain enthalpy corresponds to the energy released when the electron is coming in. So if it has a very high negative electron gain in the LP, it favors the acceptance of electron. But over here, oxygen, it does not favor the acceptance of electron, and hence it has the least negative electron gain in the LP. And boiling and melting point, it increases down the group with a small decrease at the end. You can see it in the graph. But you should note that there is a large difference between oxygen and sulfur when it comes to boiling and melting point. This is because of the atomicity. Oxygen is diatomic gas and sulfur is a polyatomic solid. Now check out this JEE Mains 2025 question, which asks us to find the reason for the large difference between melting and boiling point of oxygen and sulfur. Just now we saw that it was explained basis of the atomicity. Hence option A is the right option. Sulfur forms numerous allotropes like rhombic and monoclinic sulfur. You can check out the properties of it over here. Due to its small size and high electronegativity, oxygen exhibits strong hydrogen bonding and it has no d orbital. Hence, the maximum covalency is 4. These are some anomalous behavior of oxygen. Now, we move on to the chemical properties of group 16 elements, beginning with oxidation states. These elements exhibit various oxidation states. You can see it in the table. And the stability of the oxidation state -2 decreases down the group. And +4 and +6 are covalent in nature. And the stability of +4 increases down the group because of the inert pair effect. Oxygen shows -2 oxidation state because its electronegativity is very high, and only with fluorine it shows +2 in OF2 because fluorine's electronegativity is higher than oxygen. In case of sulfur and other elements, they show +4 oxidation state with oxygen and +6 with fluorine. Next up we have reactivity with hydrogen. They form hydrides and the thermal stability of hydrides decreases down the group, and acidic nature and reducing nature increases down the group. This you can understand by, as you move down the group, the bond dissociation enthalpy of He, that is the bond between hydrogen and the element, enthalpy of dissociation of that is very less as we move down the group. Hence, hydrogen can easily lose, and it signifies the increase in the reducing character and the acidic nature as we move down the group. Generally, the boiling point increases down the group, but as water has strong hydrogen bonding, it has the highest boiling point among this. But generally, the boiling point increases down the group when the atomic mass increases. Next, we have reactivity with oxygen, where it forms oxides of dioxides and trioxides. Dioxides, the element is in +4 oxidation state, and the oxidizing power increases down the group. You can see that sulfur dioxide is a reducing agent, but as we move down the group, TeO2 is an oxidizing agent. Oxidizing agent in that sense, it itself wants to get reduced. O3, ozone, and SO2 are gases, and SiO2 is a solid. Trioxides, the elements is in +6 oxidation state. You have to note that both EO2, that is dioxides and trioxides, are acidic in nature. Next, we have reactivity towards halogens, and they form halides. The stability of these halides are as given. Fluorine has the highest stability. They form multiple fluorides like hexafluorides, tetrafluorides, monohalides, and etc. We will see first hexafluorides. Hexafluorides are octahedral in geometry and they are gaseous. Only the hexafluorides are stable. SF6 is exceptionally stable because of its steric properties. You can see the diagram over there. It is an octahedral shape. Next, we have tetrafluorides. They have sp3d hybridization and trigonal bipyramidal geometry. But the shape is seesaw over here because you can see the lone pair over there, and the top and bottom fluorine atoms, they are repelled because of the lone pair, and it forms a seesaw shape. Next, we have dihalides, where the hybridization is sp3 and the geometry is tetrahedral. All the elements except oxygen form dichlorides and dibromides. It has a bent shape. Next, we have monohalides, which are dimeric in nature, and you have to note these undergo disproportionation, and the reaction is given there, Se2Cl2, wherein the Se is in +1 oxidation state and it is getting oxidized to +4 and reduced to 0. With that, we conclude group 16 and we move on to group 17. The halogens, fluorine, chlorine, bromine, iodine, and astatine. You can check out the electronic configuration and you can see that there are 7 electrons in the outermost shell and the general electronic configuration is ns2np5. The covalent and ionic radius increases down the group as always, and both ionization enthalpy and electronegativity is highest for the fluorine and it decreases down the group. As we move down the group, the distance between XX bond increases as the size of the elements increases down the group. Iodine size is very big, so the bond between them is also larger. Speaking about the electron gain enthalpy, it is the highest for chlorine and not for fluorine due to the small size and strong inter-electronic repulsions in the fluorine. Usually, the bond dissociation enthalpy decreases down the group, but it is bit low for fluorine because of the inter-electronic repulsions present in the fluorine. So the bond is a little bit weak and hence it is easy to dissociate. Next up, we have physical properties. Melting and boiling point shows the regular trend of increasing down the group. But hydration enthalpy, it decreases down the group. Hydration enthalpy is defined as the quantity of energy released when 1 mole of gaseous ions is mixed with water to produce hydrated ions. This element, when they are mixed with water, it produces hydrations, like the water molecules surround them. If the size is small and due to various other factors, the hydration enthalpy is very high for fluorine and it decreases down the group. Speaking about the color and the state, fluorine is gas, chlorine is also a gas, bromine is a liquid, and iodine is a dark violet solid. And solubility, fluorine and chlorine react with water, but bromine and iodine are sparingly soluble in water and they are soluble in organic solvents like carbon tetrachloride and chloroform, etc. Fluorine shows anomalous behavior because of these reasons, and these anomalous behaviors are the most of the reactions of fluorine are exothermic in nature, meaning that it releases heat, and this is because of the small and strong bonds formed by the fluorines with the other elements. When it is forming strong bonds, it releases more energy, hence it is exothermic. And this fluorine forms only one oxo acids, and hydrogen fluoride is liquid because of the intensive hydrogen bonding, but all other hydrogen halides are gases. Next, we have chemical properties of group 17, beginning with oxidation state. All halogens are -1 oxidation state. Chlorine, bromine, iodine show some other oxidation states as well. And fluorine is the strongest oxidizing agent. That is, it has the ability to oxidize others and itself get reduced. It has high tendency to accept the electron. As you remember in the previous video of physical chemistry one shot, I told you the trick oil rig. Oxidation is loss of electrons and reduction is gain of electrons. Here, it has the capacity to accept the electron. So, it is gain of electrons and it is reduction. Itself, it is getting reduced and hence it acts as a good oxidizing agent. And if you haven't checked out that video of physical chemistry one shot, please do check that out. Next, we have the oxidizing nature. This decreases down the group. Next up, we have reactivity towards oxygen, and it forms oxygen fluorides, OF2 and O2F2. These are strong fluorinating agents, and there are chlorine oxides as well, Cl2O, ClO2, etc. Other halogens, chlorine, bromine, iodine, in the oxidation state +1 to +7, they form oxides. And the stability of oxides of chlorine, bromine, iodine is in this order. The order of the stability of oxides is broccoli. This is the trick to remember this, and this was once tested in JEE mains as well. And reactivity with hydrogen, it forms hydrides. The stability decreases down the group and the acidic strength also increases. Here you can see that as the stability decreases, it can easily eliminate H ions, and because of that the acidic strength increases down the group. Acidic strength corresponds to the easiness to which hydrogen can be released. As the stability decreases, it can easily release hydrogen and hence the acidic strength increases. There is an exception in boiling point order. Usually it increases down the group, but here you can see that hydrogen HF has the highest boiling point because of the strong hydrogen bonding between HF molecules. And next we have reactivity with metals. They form metal halides, and the ionic character of these metallic halides decreases down the group. And if a metal exhibits more than one oxidation state, halides in higher oxidation state are more covalent and hence less ionic. Let's take an example over there, SnCl4 and SnCl2. In SnCl4, Sn is in +4 oxidation state. So the covalent character is higher for SnCl4 and the ionic character is less for it. I hope you got it. And with that, we conclude group 17 and we move on to inert gases, group 18. Helium, neon, argon, krypton, xenon, radon. These are the noble gases and electronic configuration is completely filled NS2 NP6. It has 8 electrons filled and it completes its octet. Speaking about the trends, atomic radii density, melting point and boiling point increases down the group and ionization enthalpy decreases down the group. It follows the regular trend. And you can see that electron gain enthalpy of these is very, very high because it is very stable configuration. And when you wanted to add an electron, you have to supply a lot of energy to make it accept an electron. Hence, the electron gain enthalpy is very high for these noble gases. Speaking about the physical properties, it is monoatomic, colorless, odorless, tasteless, and it is sparingly soluble in water. And you have to note it has very low melting point and boiling point because of the weak dispersion forces. This was once tested in JEE mains as well. And you have to note helium has the lowest boiling point of any known substance. Coming up, we have chemical properties. It is very, very less reactive because it is already very stable. And helium, argon, neon has no two compounds known. Krypton has krypton fluoride and xenon forms xenon fluorides and oxygen compounds. With that, we conclude the entire P block. I hope it was a great video. And if you liked it, please subscribe and stay tuned for more videos like this.